All right.
So, good afternoon. Good evening. You are welcome to
Good evening, sir.
302 class, that is the differential equation 2. So, I'm Dr. Salao. I will be your facilitator for this course. So, the course is divided into 3 basic topics. We are going to be looking at 3 basic topics, or let me say 5 topics altogether, divided into different. We have 3 modules, and the modules divided of ordinary differential equation.
Yes, sir.
Then the second module is the series solution of ordinary differential equation. That means series solution. So underneath, we are going to be looking at series solution of differential equation, Euler's equation, indicial equation with different root positive integers.
It's difference of root positive integer and logarithm case.
Then
Boundary value problem.
Consider Storm Levinus problem. So those are the things we have to consider in the course. So I will start straight away by going to the topic of the day, which is the solution of differential equation. I want to share your course material with you. So with your course material,
yes, I do have it.
Access it. For main time, okay.
Okay, sir.
So I would have loved to share the screen with you, but I don't have the material downloaded on this. But I will be taking you just go through the component and you go to course material. So that you have a good understanding of what it is. So series solutions. Now when you are talking about series solutions,
yes, sir.
Let's say we have a function f of s that is equal to summation n equal to 0 to infinity a n s minus this is power n. I'm using C. It all depends on the material. It's something like my own material. Now instead of they use it as S, Y, it's still the same thing. What that one defines is it defines center. If C is the center, if it is used as S subscript Y, it's still the same thing as center, as seen in some of your material.
Okay.
I will be defining it as this. So this is called a power series. And we are going to be making use of a series of this one to solve differential equation. Now, one of the things we need to do in using the series is, so when you have a series like this, the first thing we need to do is to check, does the series converge or does it diverge? So we'll be looking at the convergence or divergence of that series. So to work on it, to determine the values of S, to determine the value where this particular series will converge, then we'll make use of the definition that says so the limits as S tends to infinity. So using a n plus 1. n plus 1 into s minus c into n plus 1, and everything divided by an into s minus c raised to power n. So when this holds, we say, so when this is less than 1, we say the series converge. So when it is less than 1, so when rho is less than 1, it implies the series converge. Then if this is greater than 1, that means the series diverges. Then, but when it is equal to 1, that means the test failed.
The series may or may not converge.
Test failed. So if it is greater than 1, if it is equal to 1, the test failed. Then that's what we mean by that. Then, in another sense, when this rho, so when we have the rho that is being divided as 1 over n, So this is called radius of convergence. So when rho is equal to 1/n, it's called radius of convergence. Then to determine the radius of convergence, that means we are saying S minus C must be less than 1/L, or which is equal to R. R here is already defining the radius of convergence. So when you want to determine the radius of convergence of a particular series, then you make use of this particular formula. That is the absolute of S minus C. C is the center. C depends on textbooks.
Yes.
This is you see C as S naught.
Yes. S naught.
Either way you see, just know that this refers to, or this defines
Is the center
of the series. Then when you are doing this, that you are looking for the radius
of convergence.
So for that, when this is when it is less than, so there are other conditions that go with it. When L, this L, you know, we have 1/L. When L is 0, the series converges for all values of x. That's the meaning. So when L is 0 implies that the series converges for all values of x. Then when L is infinite, that is infinity, then the series converge only at the point s equal to c. If this L is infinity, that means the series converge only at the point s equal to c. And if L is finite, let's say any value. Now there are three cases of it. The first case is when L is 0. Another case is when L is infinite, that is infinity. Then another case is when L is finite, that is taking other numbers apart from 0 and infinity. So when you have a case like that, then the series converges. So we just say the series converges, and the radius of convergence is defined as what is given on the board. So in a series, when it comes to series, we can always carry out some operations of series. Let's consider two series now. Let's say operations on series. So I will soon take an example and check for the convergence of that series and others. But before then, let's look at operations of series. Let's say we have two series. Let's say f of s, which is defined as n equal to infinity, n equal to 0 to infinity, of an s minus c raised to power n. Now I told you this c can be anything, depends on individual. It can be, in some tests we receive as a, some tests we receive as n. One is some tests we receive no specifically the first material is as y. So I don't want to use s cos y so that I don't confuse it with x here. Then let's say we now have another series, which is d of s, that is summation n equal to 0 infinity of bn s minus c raised to power n. So these are two series. The series can be added. We can add these two series together by saying f of s plus g of s. So the two series can be added. When they are added, when the two series is added, it can be added and can be subtracted. And so when the two series, or let's say it can be added and subtracted. So when you carry out addition and subtraction of the series, this will give us an plus bn
plus bn open bracket x minus
raised to power
c n
n equal to 0 infinity. So when the two series are added together, you have something that looks like that. And again, when the series are multiplied, that is f of s times g of s. So in that case, we are saying summation n equal to 0 infinity an s minus c raised to power n multiplied by bn s minus c raised to power n. When the two are multiplied together, this can simply obtain. No, there is a constant of an, there is a constant of bn. In that case, the two constants will be cn, then this is c minus c raised to power n. So when you multiply two series, then you can have something of that. Also, we can also carry out division of series. You can say f of s divided by g of s. If g of s is not equal to 0. So if g of s is not equal to 0, then we can always also divide series. So these are basic operations that can be carried out on series. Let's now determine, so one of the questions, so these are different pieces of different operations that can be carried out on series. Apart from this, we can take some example and look how do we determine, or we can say determine the radius of convergence of a power series. Now this is a power series. Any series of this form is called power series. And this series will be used to solve differential equation. Now recall from the definition that I gave you that time. Let's say you have a series that's a function that is summation of n equal to 0 of infinity and an s minus c raised to power n. Now, for you to determine whether a series converges or diverges, or determine the radius of convergence of a particular series, then we normally there are different ways of testing the convergence of a series. You can use a comparison test, you can use ratio test, you can use the Lambert, and like that. But for this particular course, we are not going to be making use of ratio test to carry out to test whether a particular series converges or diverges. So when you carry out a ratio test, you have an and you have un plus 1 over un. If it's less than 1, we say the series. So the series this means converges. Then if an, that is un plus 1 over un, is greater than 1, we say diverges. Then if an, which is now un plus 1 over un, is equal to 1, is equal to 1, then the test fail. So when the test fail like that, then you have to look for another particular method to test whether the series converges or whether the series will converge or diverge. So when you check, once your answer is less than 1, then you know that the series converge. But if it's greater than 1, it's diverges. Then, but if your value of an is equal to 1, then the method you have used, which is ratio test, fail. Then you have to think of another method that may be applicable. Let's take an example and see and check for the convergence of that series. I will test for the convergence and I will show you how to determine the radius of convergence of that particular series. Let me take an example from your, I'll be taking an example from your first material given. So let's say u of n is given to be a series n equal to 0 to infinity 2 raised to power n, the s raised to power n, the s raised to power. So by the Lambert, if un is equal to this, then we are going to determine what will be our un plus 1. That is when you see n.
Let's add 1.
This is with, I mean, you are having a series. Sorry, you are having a series an given as this, an given as this. Okay. Our un can be 2 raised to power n, then s raised to power n. Then from here we determine un plus 1. To determine your un plus 1, anywhere you see n in your un, this is with n plus 1.
Hello, sir. Hello, sir.
That 2 raised to power plus 1.
Can you hear me, sir?
2 raised to power sn plus 1. Using the principle, the Laplace principle that says un plus 1 over un. So this will give us 2n plus 1 Sn plus 1 then over 2 raised to the power n Sn. When you have this, I can further split this. This 2 raised to the power n plus 1 can be written as 2, then 2 raised to the power n. Then this n plus 1 can as well be written as s, then s raised to the power n all over 2 raised to the power n s raised to the power n. From here, some things cancel out, then this cancels. So our an that level is 2x. There will not take the limit as n tend to infinity. So the actual definition here should be n limit as n tend to infinity. This table has to be limit attached to all these limits as n tend to infinity. So this is limits as n tend to infinity. So limits as n tend to infinity of 2x of 2. So if you look at this, there is no n here. So that shows that this is equal to 2x. X. Are we there?
Yes, you're clear, sir.
So the radius of convergence of this series, since there is no value for n, and this shows, if you look at the formula for the radius of this series converges, but for the radius of convergence, the formula says that s absolute of s minus c less than 1 over l, or which is equal to r, or you say it's less than half. Is that you say it's, or you can simply write it as absolute of s minus c less than r. So for r less the radius. So for r less the radius, what we are having here is 2s. As it is, I can, this is 2s. I can still rewrite it as this. Or simply, so if you compare this with this, you know that the position of c, which is essential, as well. So when you compare this, will now be 2 absolute of s less than r. So, or I mean, less than 1. R is your 1. So this cannot be absolute of s less than 1 over 2. When you look at what we have here, this is, so your radius is not the same thing as 1 over 2. When you look at this here, this is convergence because what we obtain is 1 over 2, which is less than 1 as defined from the definition for series. So this particular series converges, and the radius of convergence is 1 over 2. Hope that is taken.
Yes, sir. There is a part I didn't understand, sir. Are you listening, sir?
What?
Are you with me, sir?
Yes, I'm with you.
I said there is a part I didn't understand.
Okay, let me explain all about it again. Then after this particular example, I will take one more example.
No, it's about the question, the first question. You said, is it superscript n x superscript n or 2 superscript n x superscript u? Because I didn't see the superscript of x very well. What's the power of x in the question? Superscript.
Yeah, look at it from
the
this
question.
Place. Look at it from here. Look at this. From the definition, from the question given to us, we have the series 2 raised to the power n, s raised to the power n. So our u of n is taken as that. That is, so that means if u of n is this, then u of n plus 1 will be this. That is, anywhere you see n, replace it with n plus 1. That's what the thing is saying. Then, going by the formula for the absolute to come back to do To test for the convergence, we use ratio test. And the ratio test says when the limit as n tends to infinity of u of n plus 1 over u of n, if this one is less than 1, that means the series converges. Or if it is greater than 1, the series diverge. So going by that, so we now take the limit of u of n, then our u of n plus 1 is what is obtained as this. Substitute then u of n, according to the formula, that is u of n plus 1 over un. Divide.
I understand, sir.
What I did was just to split, this is 2 raised to the power n plus 1, split it to become 2, then what I have there is 2 raised to the power n plus 1. It is the same thing as 2n, then 2. So the same thing applicable to x. So when you split it, it becomes this. Then you see that 2 raised to the power n will cancel 3 raised to the power n, s raised to the power n will cancel s raised to the power n. So we are just left with 2 and s.
2 and x.
So we are left with 2 raised. So and this. So the solution reduces to this. That is the limit as n tends to infinity is 2x. Looking at this, what we have here is just 2x. There's no n appearing. So n, there's nowhere to substitute infinity for n. So in that way, the answer can just be 2 absolute s, which can simply be 2s. Actually, we are dealing with absolute. Let me clean up this side so that I can take this. So this is this. Now to test whether the series converges or not, this must be s minus c must be less than 1. So if s minus c is less than 1, that means the series converges. And this is what we have from what we are solving. 2 are what we are solving. 2 then absolute of x. So by the time you compare what we have here with what is here, that is 2 absolute of x. Now this, which I can rewrite as 2 absolute of s minus 0 less than 1. To compare. So this shows that your c, which is the center, c is now the same thing as 0. So if c is 0, then 2 that is here, because this is what the formula says, 2 is not expected, so divide 2 by 2. When you divide 2 by 2, we are going to have absolute of s minus 0, then less than 1 over 2. This less than 1 over 2 is less than 1. 1 over 2 is less than 1. That shows that the series converges. Then the radius of convergence is your, so the radius is now 1 over 2. That is the radius of convergence. So that will be this shows that this series converges and the radius of convergence is 1 over 2. So let me take another example. Maybe with that you can enhance your understanding. Another example, what with this same example, we check the question says f of s. I'm taking from your course material. Summation n equal to 0 to infinity. Then we have 2s plus 1 raised to the power n over n squared. We have this. That's for another question from the course material. So the question says we should test, we should establish whether the series converges or diverge. And again, what is the radius of convergence of that series? If you are going to do the same thing, take it from the formula, we know that the limit, that is when you are using the ratio test, limit as n tends to infinity is un plus 1 over un. So this must be less than 1 for it to converge. And if it's greater than 1, that means it's divergent. So from what we have here, our un is actually 2s plus 1 over n raised to the power 2. So what is the un? 2n plus 1 will now be 2s plus 1 n plus 1 over where you have n, replace it with n plus 1, so this will be n plus 1 squared. I will get to that point. So using that formula,
Yes, sir.
so using this on this, now that we know our un and we know the un plus 1, then the limit n tends to infinity, substitute it here, that means 2s plus 1 n plus 1 over n plus 1, where is dividing 2n plus 1 and then n squared, which you can rewrite as limit n tends to infinity of 2s plus 1 n plus 1 over n plus 1 squared n plus 1 times n squared over 2n plus 1 n squared over
2x plus 1 raised to power n.
So we have that. So the next thing from here, I can split this into 2 so that I will have it as limit n tends to infinity of 2n plus 1, then 2n plus 1 raised to power n. Then remember that is n squared, and n squared all over n plus 1 squared, 2n plus 1 raised to power n. From here, this comes
Yes.
So expanding this is s, sorry, not n. So expanding this, so this is s. So if I expand this, it will not still cancel n raised to power 2. So this will reduce to limit n tends to infinity of s squared 2s plus 1 over n plus 1 squared. Then take the limits. So what you do, expand the bracket for us to determine the limit. When you expand the bracket, n tends to infinity, this will be n squared 2n plus 1, 2s plus 1 over n squared plus 2n plus 1. So to do this, then substitute. Since we have limit as n tends to infinity, I can simply rewrite this as limit n tends to infinity, going by the principle of solving limits. This is n squared over n squared into 2s plus 1. So I'm dividing n. I'm dividing the terms by n raised to power 2. So this will also be n squared over n squared, 2n over n squared, then 1 over n squared. Once you do this, substitute your limits. Or let us write out, this is limit n tends to infinity. So the n divided by n squared, this will simply give us 2s
plus 1 over
then the down one, we have 1 plus 2 over n, then 1 over n squared. So substitute your limit as n tends to infinity. Any number you divide by infinity will give you 0. So divide this one. Once you substitute infinity to graph n, that will give you 0. This one too will give you 0. So that one will add everything together, that will give you 1. So at the end,
1
from here, it's now giving us 2s plus 1 over
1. Yes.
Are we together? So let me click.
Yes, sir. Yes, sir.
Ask space to continue. Since I'm having this, so this can simply be 2s plus 1 in this. And I can simply rewrite, is this one less than 1? Or I can simply rewrite this as 2 into s plus 1 over 2. What I have here is the same thing as this. So to test whether this is converges or not, remember the formula says once the un plus 1 over un, the limit of n tend to infinity, once it's less than 1, the series converges. So, and again, on the ratio, to test for the radius of convergence, it must be s minus c, then less than 1. If you compare what is found inside this bracket, inside this absolute and this, you will see that your c is not the same as minus 2. So I make this into look like this. I will have 2 into s plus 1 over 2 less than 1. Divide 2 by 2 so that this can simply be s plus 1 over 2 and 1 over 2. Since what we are having here is less than 1, that shows that the series converges. And the radius of converging is written as 1 over 2. So the radius of convergence R is now 1 over 2. So that's how. So we are only fortunate that the first example I saw, we have 1 over 2 as the radius. Solving these two, we have 1 over 2 as radius. It's not in all cases you have it as 1 over 2. The radius depends on the series given to you. But for this particular question that was solved for the first and the second one, we have the radius of convergence to be the same. That is 1 over 2 and 1 over 2. And then over 2. Are you okay with this? Any questions?
Yes, there is a question, sir. There is a question, sir.
All right.
What's it called? The last part, the limit of n as it approaches infinity is 2x plus 1, right? So we made the absolute value to be 2 open bracket or 2 absolute value x plus 1 over 2 less than 1, right?
Are you referring to what I wrote up here?
No. The last one you did. The last one you did. The last one you did, which we made them 2x plus 1.
This one?
The absolute value.
That is absolute value of 2x plus 1. I mean?
Exactly. Yes.
Yes, when you take 2 out, it's just like bracket now.
I understand.
I'm treating it as a bracket. That is.
Yes, okay.
So it's just as if you're having 2x plus 1 in bracket. So when you bring these two out, this is the x plus 1 over 2. If you open the bracket, you see that you go back to this.
Exactly.
Are you okay?
Yes, sir. So that same 2 we brought out, what happened to it? Did we divided it by 2? We divided both sides by 2, right?
We formed the to test for radius of convergence. I've given you now is still in the course material. The radius of convergence is s minus c less than 1 over n, which is written as half. Or which, instead of writing it this way, you can simply write it as s minus c less than r. I mean, then for convergence, it is expected that s minus c is less than 1. So when s minus c absolute is less than 1, you say the series converge. But when it's greater than 1, you say the series converge. Then going by what we obtain from our solution, we have it as 2 into s minus plus 1 over 2, like this. So when you compare, we have to check whether this thing. What I have is 2 into s plus 1 over 2 and less than 1. So that it will look like you want to test for convergence. So this is the formula to test for whether once your series satisfies this, you say it converges. And this is what we have. I have to write it to look like the first one. Just like the first one that I did the other time, here we have 2 absolute of s. If we check, I rewrite it as 2 s minus 0, then less than 1. And I later divide through by 2.
0.
So the same thing I'm doing here.
Yes.
So that I have to express it this way, so that it can satisfy the expression or the definition for convergence. So when you look at this now, my c that is here, not the same thing as minus 1 over 2.
Yes, minus half 1 over 2.
So ordinarily, you are not expected to have any value outside the absolutes, but we are having 2 in this case. So we need to eliminate that 2. To eliminate the 2 is to divide 2 by 2. So when you divide 2 by 2, 2 will divide here. Then I will have s plus 1 over 2 less than 1 over 2. And what we have here is less than 1 over 2. Once what your answer is less than 1, that shows that the series converges. They converges. And the radius of convergence now, the radius, it converges, then the radius of converging or convergence is now the same as 1 over 2.
Why the center is minus 1 over 2?
Compare, look at this. Look at what I have here and look at what is here. Just look at the one inside the bracket. I mean the absolute line, this and this. If you compare, this is minus c, this is plus. Yes. So minus c is equal to 1 over 2 when you compare. I mean, this is simply that c is equal to minus 1 over 2. So C, which is your center, a question can be given to you that will say determine the center. Is the series converged? When you say yes or no, determine the center. What will be the value of the center and at what radius will it converge? So the center is minus 1 over 2 and the radius 0. For the first example, the center is 0 because this is what we obtain.
Yes.
So this shows that the center is at the origin. So that's why if you add this and write it as this, you are still saying the same thing. So when you now compare this with this, you will see that your C is now 0 in this case. While your R is now half. By the time you compare this and compare this, you see that your R is now 1 over 2. So that's how to determine the radius. To check whether a series converge or diverge, and check the radius of convergence of that series. Is that taken?
Yes, sir. Yes, sir. I understand, sir.
So that will now take us further to definitions of series or remarks, or let me just say a simple remark on series as taken from the mass area. So remarks, that is, change your summation. When you have a summation, no, the series that we are looking at, there is a summation there. There's a way you can change the summation. So we want to look at change of summation now. Change of summation of a series. So look at the first example. Let's say you are doing a series s equal to 0, infinity, an, s raised to power n. I can move n equal to 0 to infinity. The summation of n equal to 2 to infinity, an, s raised to power n. In a case where you want to return, instead of having 2 here, and you want it to start from the origin, that is from 0. Instead of having 2 here, look at the basic way of going about it. So this one is the same as it is the same thing as summation n equal to 0, infinity of an plus 2, then sn plus 2. So because this one is equal to 2, but in a simple way, so that I don't have to confusion along the way. Let me just show you how to go about it. Look at what is here. We have n equal to 2. Let's say this n, when you take it to this other side, you become n minus 2. Let n minus 2 equal to n. To say. So I can now write this. This implies that n is now equal to n plus 2. Now substitute where you have n here in this expression, substitute it to be n plus 2. So I can now have this solution as n plus 2 is equal to 2, because where I have n is now m plus 2. Infinity. This is n. This is now m plus 2. This is n here. This will give you m plus 2. Now, if you look at this summation, that is n plus 2 equal to 2. I can take this 2 to the other side. Then that will give me summation m equal to 0, infinity, am plus 2, and sm plus 2. So that is the change of summation. So from n equal to 2 to infinity, we can now change it to n equal to 0 to infinity. So when you look at what I have here and look at this, they are not the same. Only that I wrote this one in terms of n, and this one is written in terms of n. So that's how to go about change of summation. Let's look at another place. Another one. Let's say that giving summation. N equal to 2 infinity. N minus 1. An. Then Sn minus 2. If you have to do the change of base for this particular one, anywhere you see n, change it to n plus 2. Because what we have here is n equal to 2. The summation n equal to 2 to infinity is n bracket n minus 1 an s base of power n minus 2. So for you to change the base, if you want to change the base to 0, if you want to change the base to 0, anywhere you see n, replace it with n plus 2. You will see that the base will change to 0. Once you do that, anywhere you see n, you change it to n plus 2. So here we have the summation n plus 2 equal to 2. That is, I want to change the base. Anywhere you see n, change it to n plus 2. Plus infinity. Then we have n here. This will be n plus 2. I have n minus 1 in bracket. This will be n plus 2 minus 1. Then an plus 2. And s will now be n plus 2 minus 2. Bringing them together, simplifying that. This n plus 2 equal to 2. When 2 go to the other side, that will reduce to n equal to 0 of infinity, n plus 2. Then this is n plus 2 minus 1. That will give us n plus 1. Then an plus 2 s. Then this is n plus 2 minus 2. This is just the base of power n. So you can see that the base has changed. The summation has changed from n equal to 2 to n equal to 0. This is very important that you know it, because by the time we get to solving using power series, solving differential equation using power series, we always do change of base, change of summation index. So that's why I'm taking my time to just explain this to you. So by the time we get there, it will not be new to you. And these are what I've done here. We have been changing from 2 to other values. You can change from 2. In fact, if you don't want to change to this is 2, you can change it to 1. It depends on you. It will satisfy it. But let me take another example where we have summation from 0 to infinity, and we want to change it to 2 or 1 or 3. It will satisfy this. So this is very important, because when you get to series solution for power series, for differential equation, change of base, change of summation index is very, very important. Let's look at another case of example. Let's say you are doing summation n equal to 0. Infinity, an, then Sn plus 2. You want to change it to summation 1. You know it's starting from 0 now, but you want to change it to summation 1. When it was starting from 2, we are adding, we are changing n to be n plus 1. But when you want to change it, the summation to, let's say from 0 now, you want it to move to 1. Anywhere you see n, replace it with n minus 1. That means you want to change the summation from 0 to infinity to 1 to infinity. Then anywhere you see n, replace it with n equal to n. Anywhere you see n, replace it with n minus 1. If you do that with this particular one, we are going to have summation n minus 1 equal to 0 infinity a n minus 1. Anywhere you see n, it is n minus 1. S n minus 1 then plus 2. When you look at this summation, I can say this n minus 1 equal to 0. I can rewrite this as n equal to 1. Infinity a n minus 1 then s minus 1 plus 2. That will give us plus 1. I mean, so this is giving me plus
Yes, sir.
1. N plus 1. So you can see that I've successfully moved the summation from 0 to 1. So that's how to change the summation. Then you can even say, oh, from 0, I want to move it to 3. All you need to do anywhere you see n, replace it with n minus 3. You will see this and it will come up. Let's say what we are giving n equal to 0, infinity a n s n plus 2. And I want to change this to start from, instead of starting from n equal to 0, I want to start from n equal to 3. All you need to do is anywhere you see n, just replace n with n minus 3. That if I want it to start from 3. If you do that, this will be summation n minus 3 equal to 0 infinity. There's n here. This is n minus 3. The s n minus 3 plus 2. Simplify this, taking this 3 to the other side, this will give you summation n equal to 3 infinity a n minus 3 s 3. Then we have minus 3 plus 2. That will give us minus 1. So this will be n minus 1. You can see that I've successfully moved the base from 0 to 3. Are we okay with that?
Yes, sir.
Is there any question on it? So that's how to change the base of the summation. This is very important that you take note of it, because by the time we get to application using power series to solve differential equation, this and many more are things we are going to be coming across. So the next one we considered is what is ordinary point, singular point of a differential equation. We now look at ordinary and singular point of a differential equation. Ordinary and singular points of a differential equation. Ordinary and singular point of a differential equation. Let's consider a differential equation of the form. Consider D of the form Px y prime, and that's of second order, plus Qx y prime plus Rs y equal to 0.
Equals 0. Equation 1.
So when Q of when P of S, when P of SS naught is not equal to 0. When P of S naught is not equal to 0, the point is called ordinary point. And as such, S equal to 0, S naught is analytic. S naught. So when you have this P of S, that's what I'm saying now, that if S is equal to S naught, and you replace this P of S here with S naught, if it is not equal to 0, that is what we call ordinary points. And at that point, S equal to S naught must be analytic. When the function is analytic, that means the function is differentiable. So take note of that. But when of S naught is equal to 0, it's called singular points. when P of S is equal to 0, it's called singular point. But when it's not equal to 0, it's called ordinary points. And at those points, S equal to S naught is analytic. And that's what we mean by ordinary points and singular points. Do you have any questions so far?
No, sir. I understand all of them.
Okay. Now, we cannot go on to solve, to apply power series to differential equation. There are two cases of it that we are going to look at. We are going to look at solution near an ordinary point. And we are going to look at the solution that's not an ordinary point. Now you know what an ordinary point is, and you know what a singular point is. So it's either you look at solution at ordinary point or at regular singular point. But at each point, S equal to S naught is analytic. Are you okay with me?
Yes, sir.
Okay.
Yes, sir.
So now, for us to solve any differential equation with using series method, so we are still going to be considering this particular equation given to you, P of S of y prime prime. I mean, we are talking about second order differential equation. If I divide through by P of S, so that we have y prime prime plus Q of S over P of S y prime, then R of S over P of S y equal to 0. So this can be y prime prime plus, I can say capital Q of S y prime plus Q of S y equal to 0. That is, P of S is written as Q of S, P of S, and Q of S is written as R of S over Q of S. So we now are dealing with y prime prime plus P of S, this is capital P, S y prime plus Q of S y equal to 0. So to solve
please,
this particular equation using power series method, we are going to say let y equal to summation n equal to 0 infinity an s raised to power n. So we take this. So to solve any differential equation using power series method, we are going to be making use of this series solution, that is y equals to summation n equal to 0, n equal to 0 to infinity an s raised to power n. So the next thing is to take the first derivative of your y, differentiate this. This will give us summation n equal to 0 infinity. We are differentiating with respect to x. This will be n, an, s, n minus 1. I think you can still remember your method of differentiation. This n will come and then subtract 1 from it. So the first prime will be also the second derivative, prime will be summation n equal to 0 infinity n into n minus 1 an s n minus 2. So to solve a differential equation using power series, we are going to be making use of that by defining our y prime. Our y will be this, y prime is this, then this is y prime prime. So all you need to do is to substitute into the differential equation that's given to you, then simplify,
what you are doing.
and you obtain a kind of series. You obtain the solution in the form of series, which you obtain a recurrent solution for it. So let's take a clear example and solve using power series method. So I'm taking this very example. The question says, solve the equation near the ordinary point s equal to 0. Solve the equation y prime prime plus 4y equal to 0 near the ordinary point of s is equal to 0. So this is a simple question that we can solve. But because of my time, I will stop here. By next week, I will take the examples and I will take other examples on series solution. So that means by next week, we are now going to be looking at solving differential equation using the series method. So, do you have any question?
I can't see what you are doing, sir. I can't see what you are doing.
Can you see now?
No.
I only wrote a question on the board. I've not solved any question. I picked a question to solve using power series method.
I know. From my end, it is black from my end. I can only see dark surface from my end. I can't see anything aside from that. Yeah, I can see it now.
Okay. So, because of time, I will not be able to solve the question and the problem today. So by next week, I will go on to solve the next week.
Okay.
So
okay, sir.
In the absence of questions, I want to bring the class to an end. And why
okay,
we continue next week the same time. So please
sir.
encourage others to join the class as when due. It remains 5 to 6 with the same link. Please take note of that.
Sir.
So see you next week.
All right, sir. Bye-bye.